So now we'll see how we can apply these ideas very directly to the language modeling problem. So, and we'll see how trigram language models can be derived as a direct application of second-order Markov processes. So a trigram language model will consist of two things. Firstly, we'll have some finite set V, which is just going to be the vocabulary in the language model in exactly the same way as before. So it might have words like the, a, Beckham, and so on and so on. Again, this might be a fairly large set, might be a few thousand, or even a few tens of thousands of words. And then the second part of a language model is a set of parameters. So for every sequence of 3 words, UVW, so this will be referred to as a trigram, a sequence of 3 words, we have a parameter QW given UV. We'll see very soon the role these parameters take. W could be any element of V, or it could be the stop symbol, and U and V could be any element of V in addition to these special start symbols we saw in a second-order Markov process. And given these definitions, the model defines a distribution as follows. So for any sentence x1 through xn, where each xi is in V for I equals 1 to n minus 1, and where xn equals stop, the probability under the trigram language model is defined as a product of terms. So I have I equals 1 to n. At each point, I have q of xi given x minus 2, x minus 1. I'll illustrate this in a second with an example, but basically these parameters correspond directly to the probability that xi is equal to xi given xi minus 2 is equal to xi minus 2 and xi minus 1 is equal to xi minus 1. So this is basically just a rewrite of the second-order Markov process I showed you in the previous section. So that's the formal definition, but things should become a lot clearer if we go through an example, because what we end up with is really a very simple model. So let's take a particular sentence, for example, the sentence, the dog barks. As before, we have the stop symbol at the end of the sentence. We'll always have that. So in this case, the probability assigned to this sentence under the language model is a product of terms. So you'll notice that we have each of the words, the, dog, barks, and stop. And at each point, we condition on the previous 2 words in the sequence. So for example, barks is conditioned on the and dog because those are the previous 2 words in the sequence. So what we're doing here is essentially treating sentences as being generated by a second-order Markov process, where each word in the sentence is chosen conditioned only on the 2 previous words in the sentence. And that is a trigram language model. So let's just talk briefly about this assumption that each word depends only on the 2 previous words. So that clearly is a very naive assumption. And in fact, it's possible to construct all kinds of examples where that independence assumption is very clearly violated. And in fact, later in the course, we will see models, for example, probabilistic variants of context-free grammars, which are arguably much more realistic models of language in that they capture much longer range dependencies than just the previous 2 words in the sentence. Having said that, trigram language models are tremendously useful. It turns out that they are quite difficult to improve upon, and they have the benefit of considerable simplicity in that all you have to do is estimate these trigram parameters in the model. This estimation problem we'll come to a little later in this lecture. But to summarize, For any sentence, its probability is a product of terms. We have one of these Q parameters for each trigram in a sentence, where we condition each word on the previous two words. So this leaves us with a remaining estimation problem, which is that we want to estimate these Q parameters in the model. So, for example, we might want to estimate the probability of laughs, given that the previous two words were the and dog. And we'll spend quite a lot of time on this estimation problem, and it turns out to be quite a challenging problem. Let's first talk, though, about a very natural estimate for this quantity, and this is often referred to as the maximum likelihood estimate, and it's really a very intuitive estimate. So recall again that we've assumed that we have a training set. So we have some example sentences in our language. We might typically have maybe a few million, or a few tens of millions, or maybe even a few billion words or sentences. From these training examples, we can derive counts. So for example, count of the and dog would be the number of times I've seen the word the followed by dog in my training examples. Count of the dog laughs would be the number of times I've seen the trigram sequence, the followed by dog, followed by laughs. And the maximum likelihood estimate, which I've written here for this example, is the ratio of these two terms. So I have the ratio of the trigram divided by the ratio of what we often call the bigram, the sequence of two words that we're conditioning upon. And that's a very intuitive and a very natural estimate. Many people would have come up with this as a first guess for how to estimate the parameters of this model. So maximum likelihood estimators will be very useful. They will form the starting point of the estimation methods we will develop. But they do have a very clear problem, and that is the following. We have a huge number of parameters in our model. Even though we've made this assumption that we only condition on the previous two words at each point, we still have a very large number of parameters. So if we define n to be our vocabulary size, well, there are n possibilities for this word, n possibilities for this word, n possibilities for this word, plus one or two if we take the stop symbol and start symbols into account. But as a good estimate, we have n times n times n. We have n cubed parameters in the model. And so, for example, if we have a vocabulary size of 20,000, we have 20,000 cubed. That's 8 times 10 to the 12 different parameters. So that is a very large number of parameters, irrespective of how much training data we have. This is going to be a very large number in comparison to the number of training examples that we have. And this manifests itself in the following way. In many cases, this count on the numerator may be equal to 0, because we simply haven't seen this particular trigram in training data. And in that case, this estimate will be equal to 0. That's problematic because there are so many trigrams possible, maybe 8 times 10 to the 12, that just because we see a trigram 0 times in training doesn't mean that we should say this estimate is equal to 0. Worse still, in some cases, this denominator may be 0. Maybe I've never seen the words the followed by dog. And in that case, this ratio is completely undefined, and the estimate really falls apart. So the main point here is that we have a very large number of parameters. We have a large amount of training data. That will mean that many of these counts are equal to 0, and that will lead to estimates being unrealistically low or actually ill-defined. But we'll soon see that we can modify these style of estimates in ways that make them quite robust to these problems.